Now we're starting the segment on integration. Our first integral falls into the category of a secant tangent integral where the exponent of tangent is odd. And what we do in this case is we put secant tangent next to the dx, secant x tangent x, next to the dx. That's the derivative of secant x. All right, so we pulled off one tangent x, so we're left here with tan squared x, and we also pulled off a secant x. So, well, what do we do? Well, what we have here is we'll put secant 2/3 x, and to make up for the secant x that we wrote next to the dx, we'll divide by secant x. So you see these cancel, and we're left with what we have above. But let's combine these. Let's subtract 2/3 minus 1. That's 2/3 minus 3/3. So we have secant to the minus 1/3 x, tan squared x, secant x tangent x. Okay, now next to the dx we have the derivative of secant, so we want to switch everything else to secant. So tan squared, let's recall the trig identity that we're going to use over here, and that is tan squared x plus 1 is equal to secant squared x. So tan squared x is equal to secant squared x minus 1. So we're going to replace tan squared with secant squared minus 1. And at the same time, let's do our u substitution. We want u to equal secant x, so that du is secant x tan x dx. And now we're ready to do our u substitution. So we have u to the minus 1/3 times u squared minus 1. And all this is all du. Okay, so we're going to use the power rule once we multiply through. U to the minus 1/3 times u squared. That's u to the minus 1/3 times 6/3. So I'm adding minus 1/3 plus 6/3. That's u to the 5/3 minus u to the minus 1/3 du. Okay, now we're ready for the power rule. Okay, so we have u to the 5/3 plus 3/3, that's 8/3. Divide by 8/3, and multiply by 3/8. And here we have minus 1/3 plus 3/3, that's 2/3. And divide by 2/3 and multiply by 3/2. And now we'll just substitute back u is equal to secant x, so we have 3/8 secant x to the 8/3 minus 3/2 secant x to the 2/3 plus c. Our second integral is a u substitution, where u is a linear function of x. So there we have it right there. And what this will do is we'll end up with a single power of u in the denominator, and then we'll be able to divide into the numerator and split this up. All right, so we're going to put u equal to x minus 2. du is dx. And then we're going to need u plus 2 equal to x. All right, so let's do our substituting right now. So in the denominator we have u to the 3/2. And here x is u plus 2. So in the numerator we have u plus 2 plus 1. So that's u plus 3. And dx is du. Again, what we did there, x was u plus 2. So that's u plus 2 plus 1. That gave us the u plus 3 in the numerator. Okay, now we'll split this up, divide u to the 3/2 into the numerator so that we can use our power rule. So we have u to the 1 divided by u to the 3 halves. That's 2 halves minus 3 halves. So we get u to the minus 1 half here, plus 3 u to the minus 3 halves du. Okay, now use the power rule. Minus 1 half plus 2 halves is 1 half. Divide by 1 half or multiply by 2. And now we have u to the minus 3 halves plus 2 halves, so we have a minus 1 half here. Divide by minus 1 half or multiply by minus 2. And then we have the 3 right here. And now we can just substitute back. We have u is equal to x minus 2. So here we have 2, x minus 2 to the 1 half, minus 6, x minus 2 to the minus 1 half, plus c. Our third integral is a typical integration by parts. All right, and we'll put u equal to x, and du is dx. And we'll put dv equal to e to the 5x dx. And v is equal to 1/5 e to the 5x. Okay, now we're going to do uv minus the integral of v du. uv this way. uv, that's 1/5 x e to the 5x minus the integral of v du. Okay, I'll put the 1/5 on the outside. E to the 5x dx. All right, so that's 1/5 x e to the 5x minus 1/5. And now this integral is 1/5 e to the 5x. In this integral, we have 1 plus sine x in the denominator. And one little trick that we do in this case, if we have 1 plus sine x or 1 minus sine x or 1 plus cos x or 1 minus cos x in the denominator, sometimes it helps to multiply top and bottom by whatever's in the denominator with the opposite sign. So in this case, we'll multiply top and bottom by 1 minus sine x. Okay, because then in the denominator we end up with 1 minus sine squared x, which is cos squared x. So we did this so that we end up with a single term in the denominator. And now we could divide into the numerator with this single term, split up this fraction. So let's do that. So we have 1 over cos squared x minus sine x over cos squared x dx. All right, so let's rewrite this. So this is secant squared x. I'll split this up into two integrals. Secant squared x dx minus sine x over cos squared x dx. Now, we know what the first integral is because secant squared is the derivative of tangent. So we have tan x. That's what we get when we integrate the first integral. And the second one, we could do a u substitution. Let's put u equal to cosine x. And so du is minus sine x. We have it right here. So we end up with u to the minus 2. And du is minus sine x. So let me put a plus over here and write du. So minus sine x dx. That's du. Du is equal to minus sine x dx. All right, so that's all that is a plus du. Now just do the power rule. So we have, let's carry along that tangent x. So here we have u to the minus 1, just adding 1, and then divide by minus 1. Okay, so we have tangent x minus 1 over u, and u is equal to cosine x. Number 5 is a typical arcsecant. All right, so let's write this as, let's say we have a 2x here, and here we have 2x squared minus 5 squared. All right, so let's put u equal to 2x. And 1/2 du is equal to dx. So here we have 1 over, and here we have u, square root, and here we have u squared minus, I'll write this as 25. And then for dx, we substitute 1/2 du. Okay, so let's just use our arcsecant integration formula. So that would be 1/2, and here we have arcsecant, the absolute value of u, over a, which in this case is 5. And we multiply by 1 over a, that's 1 over 5 on the outside. Okay, so now just substitute back, and we have 1/2 times 1/5 arcsecant, absolute value of 2x divided by 5 plus c. In number 6, we have an improper integral, and it's this infinite limit over here that makes it improper. Okay, we're going to integrate this using integration by parts. We'll put u equal to x, and du is dx. And we'll put dv equal to e to the minus x dx. And v is equal to minus e to the minus x. All right, and then we use uv minus integral v du. Okay, so here's uv. Here's uv. So that's minus x. I'll write that as minus x over e to the x. And we're going to evaluate that between 0 and infinity. And then we have minus v du, so that will be plus the integral from 0 to infinity, e to the minus x dx. Soon we're going to be substituting r for infinity and taking the limit as r goes to infinity. We'll do that soon. But in the meantime, let me just integrate that last integral over there. Okay, so that will be minus e to the minus x. So I'll write it as minus 1 over e to the x. And we're going to evaluate between 0 and infinity. Now let's replace infinity by r. All right, so what we're doing is we're going to take the limit as r goes to infinity, minus x over e to the x, minus 1 over e to the x. Okay. All right, let's continue. Let's substitute in r, so we have minus r over e to the r, minus 1 over e to the r. And now substitute in 0, so we have well, maybe I'll just put a minus in front of this whole thing. So when we substitute in 0 into this first term, we have 0. And here we have 1 over e to the 0. All right, well, let's just know this 1 over e to the 0, that's 1 over 1. So this fraction is equal to 1. Okay, here, as r goes to infinity, well, 1 over e to the r goes to 1 over infinity. So this is 0. Or this goes to 0 as r goes to infinity, and this one does as well. This also goes to 0, and we'll see that by using L'Hopital's rule. We'll do that soon. All right, so assuming that these both go to 0, what we have here is minus minus 1. So our integral evaluates to 1. Let's just finish the calculation by doing L'Hopital's rule to show that r over e to the r goes to 0 as r goes to infinity. So we're going to do that here. All right, so we're going to take on the side, let's do the limit as r goes to infinity. We can do, let's say, minus r over e to the r. Well, notice that the top is going to infinity and the bottom's going to infinity, or the top's going to minus infinity. In any case, this is an integral, a limit of the form infinity over infinity. So we can use L'Hopital's rule, differentiate top and bottom. So we have limit r goes to infinity, minus 1 on top, and e to the r on the bottom. So now we no longer have something of the form infinity over infinity. This is actually, we have the top stays at minus 1 and the bottom's going to infinity, so this limit is 0, like we said. Okay? All right, so that finishes the calculation.